Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today, I'm pretty excited. We have EPC in the lab, efficient power conversion. They're the guys that make GaN FETs. They call them the eGaNs, the enhancement mode GaN FETs. Really cool stuff. Now, I kind of met them because I was asking them about their products in the past. I got some eval cards to do some other testing, and I got an email and they said, hey, we got a new eval card. Do you want it? You want to try it out? I'm like, heck yeah. So these vendors, they will do that. They'll give us engineers, like I'm a power engineer, so they'll give a guy like me a board like this because they hope that I'll use their products in my designs, which, you know, someday I hope to, because I want to use some GaN FETs. So I started doing some designs with GaNs and really anxious to get them on a board and actually get my designs going. But they sent me this and I'm excited to try it out. Now, what I want to do is I want to explain something about this, what's so cool about it, and kind of show you how the technology, how the future of power electronics is GaN FETs. I kind of did a video on that before. I'll put the link down below. But you know, people love standards, right? Like these 19-inch racks, the ATX power supply for PC computers, you know, the desktop ones. You know, there's all these standards, DIN rails, you know, a bunch of different standards have come out over the years, and as technology improves, things get smaller and smaller. Now, part of those standards are the physical package, because in this case, they call them bricks. They'd like to take what this is called a full-size brick and plug it into a board and just have it work, and have the pins that are on both sides, the inputs and outputs, match another vendor, so they could say, we got a better price from these guys, we'll pull this one off and use this one, you know, in the new product or whatever. So that's the idea. Then they don't have to hire guys like me to design discrete designs, power supplies. They can just plug and play with modules, and in some cases you can. They still need guys like me to, and that's why they sent me this, because, you know, I might use some modules in a design, but more than likely I'll use their circuitry in some of my designs and just modify it if I need to, right? So that's kind of the idea of sending out eval cards. And this is a full-size brick. I've had this around forever. It's 200 watts. So when you talk about the technology, and if there's, say, around 11 square or cubic inches in a full size, then that's less than 20 watts per cubic inch. Well, the industry's been closer to 50 watts per cubic inch for a while now. Okay, so now with GaN FETs, that power density is shrinking big time. Well, even today, before GaNs, you could get 500 watts out of a full brick. Okay, so over 20 years or whatever it's been since I've had this in my toolbox, the industry's improved. 50 watts per cubic inch. So if this is 10 inches, that'd be 500 watts. So that makes sense, right? Well, now you get something like this. Let me just go back to the physical size. Half-size brick, quarter-size brick, or even the 8-size brick's been pretty common, but you can imagine the power drops with each size, but you might only need 100 watts or 50 watts, so you get a smaller size brick, right? Well, now you get a 16th brick. Well, and they've probably been out for a little while too, but let me just show you what that looks like, because it's pretty darn cool. That's the little motherboard to test. It's got all the test connectors. It makes it look big. But that's a 16th of a brick. 1/16 of a brick. That's crazy. I believe it's like 1.1 or 1.2 cubic inch. Okay? So that is teeny. But now here's the impressive part. That's 300 watts. So 300 watts you can get out of that. Now if that's not efficient, then this thing is going to be just super hot, and it's going to be hard to blow enough air on it or to run cooling. It's going to be hard to cool it. So that 50 watts per cubic inch, that's a realistic value that you can cool and all that kind of stuff. Well, now 300 watts in, say, 1.2 cubic inch. Okay, so that's nuts, right? That's a lot of watts. They can do that for a couple reasons. The packages have gotten small, but the efficiency's gotten high. So those two things together allow you to put a really small package and be able to cool it. And you put it on a little board like that, send it off to engineers like me so I can play with it and test it out and get all impressed, which I am. I'm super impressed. Hey, what I want to do is I want to show you guys the schematic of this motherboard the EPC came out with. Super cool. And I want to show you the actual schematic for the 16th inch brick and datasheet for the little GaN FETs. There's 4 FETs on that. Can you believe it? 4 FETs. That's just nuts. One thing that's super cool about GaN FETs, like in my video I talked about before, that I'm going to put a link on, is GaNs are super small, but the thermal interface, there's almost no thermal resistance, very little thermal resistance from the actual, die or the FET itself. It almost looks like a die when you look at it. It doesn't look like a plastic package like normal FET. So they're efficient, plus they get rid of heat fast. So what heat they do gather, they can shed off quick. So yeah, anyway, let's go through the documentation, and then we're going to come over here and do some testing. Guys, I just wanted to show you, close up so you can see to scale with my hand the size of this thing. You can see the banana jacks. That makes it easy. All the test connectors. Now, here's some aluminum electrolytics just for bulk capacitance. Now, of course, they don't know what kind of power supplies people are hooking up. So, they try to account for that. And then there's some ceramics down here. You saw in the schematics, but that's what it looks like. Okay, and if I pull this off, there's the standard size pins, nice machined sockets. So here, I'll show you a close up of this in just a moment. Now, here's what various different GaN FETs might look like. And you can see this old module here I've had for like evers. Yeah, these guys, they wouldn't be happy with me showing you this thing because they've improved their technology a lot. And I wouldn't be surprised if they have a lot of GaN technology. Well, I'm sure of it. Anybody doing modules or doing GaNs these days, or at least it's in the works. Okay, and here it is mounted on our little motherboard. Pretty neat, right? Just want to show you a close-up before we start testing. Alright, the size comparison of 16th brick to full-size brick. Okay, this is EPC's website, Efficient Power Conversion, and here is the development board. Pretty darn cool. One thing I want to point out, this large card is a development board, and that is what they call the test fixture, the EPC9534. This little teeny brick in here is the 1/8 inch brick eval card, and that's the EPC9157. Then efficiency greater than 95%. And that's a 12 volt output, 25 amps out of that little guy. That's crazy. Now you can see the size there. It's just over 1 inch square. That's the 16th inch brick format. So it's the standard industry footprint. And this guy is set up to operate at 500 kilohertz. And it's running with this chip up here from Renesas. It's the ISL 81806. And it can run up to 80 volts. It's a dual synchronous buck converter. Let me show you that real quick. So this is Renesas website, and this is the chip. This is just the quick little feature list. So just show you there. Has all bunch of cool features, and it can run 100 kilohertz to 2 megahertz, which is just nuts. Has the gate drive for GaN FETs. It's specifically designed for GaN FETs, although I'm sure it'd work with Mosfets, but it's designed for GaN FETs, so you don't need an extra driver. Pretty darn cool. Okay, back to this guy, the EPC9157, 300 watts. That's just nuts. Now here's efficiency curve. Now what you'll notice is at 36 volts, you get a little more efficiency. So 95%, let's say right here, and 1% more with 36. Because you're not dropping the voltage as much. You're going from 36 down to 12 instead of 48 to 12. So that makes sense, right? But what's really neat is all the way down to what? 4 amps, 3 or 4 amps, you're still above 90%. So a lot of times when you're at a small fraction of whatever the rating is, your efficiency starts to take a dive, which this does, but that's only because it's blown up from 90 to 97. But capable of 25 amps, and even just below 5 amps, it's still giving 90% efficiency. That's pretty cool. All right, guys. So here's the GaN FET. That is what the die looks like. Isn't that nuts? I mean, it's small, 3.5 millimeters by 1.95 millimeters. And it's just these guys are just teeny. And those are the actual things that get soldered to the board. Pretty cool. 100 volts, 3.2 milliohms, 60 amps, and it can pulse up to 231. Now, what they're not showing you is all the other specs, the capacitance, the gate drive, you know, how efficient these guys are to turn on and off, and also because of the real small package, how small the thermal impedance is between this and your board. So it gets rid of heat real fast too. Okay, so here's the full data sheet. All right. And look, here's some of the applications: Class D audio amplifiers, AC to DC converters. So, I mean, you know, there's a lot of uses for this because of the voltage and the current capability. Here's the thermal impedance I was talking about, 1/2 degrees C per watt. That's pretty darn nice. And from junction to board, it's only 1.4. So, yeah, it's really cool. Now here's the total gate charge. It's just barely over 10 nanocoulombs, or 13.6 maxed. So, yeah, these guys are really impressive. Just showing you the curves real quick. The gate turn on, it looks like a Mosfet, right? This is 2 volts. Above 2 volts, it starts ramping up again. But the main thing you want to compare this to a Mosfet. See right here, this is only 2 nanocoulombs, just over 2. And from 2 to 4 nanocoulombs, you have this little step. That's really small in comparison to a FET with the same kind of capabilities. Okay. Okay, now this is this schematic of that board, and what it's showing is here's a little 16-inch module that goes on it, and what they're doing is they're supplying you with electrolytic 80 volt 47 microfarad on the input, and on the output over here 220 microfarad 25 volts. There's also these 10 mic ceramics up here, and on the input there's the 1 mic ceramics. So you want those ceramics parallel, you know, several of them, to lower the impedance, keep that noise down, right? Okay, so that's what that schematic looks like, and that's what the board looks like. And they're saying for 300 watts, that's a lot of power. Even how efficient it is, it's still a very small place to get rid of that heat. So they're suggesting convection cooling in this direction. And there's the test setup. Okay, so remember, convection cooling comes this way. All right, and this is the schematic. Here's a controller right here in the middle. You got your input caps on the left, your output caps over here on the right, all down here in row. But now what you notice right off the bat is, see, there's 2 GaN FETs up here on top with L1. That's one of your buck converters. And then you have your other buck converter down here, and they're tied in parallel at the output. So this guy can actually drive 2 buck converters, and in this case they're parallel together. Pretty cool. Pretty teeny design. And this was a press release on this device. So, pretty new device. Alright. Hey guys, so let's just go over this setup, just so you can kind of see what I'm doing. I've got the card here. Input power is coming in here from my power supply, okay? And then I'm picking up and going to the meter here, so you can watch at the same time I'm doing it. And then on the output I've got a meter, so you can watch that voltage. And then it comes up to this little load, and I'm using this load so that you can kind of watch, so you can kind of see everything going on in one picture. And then I use this Kaiweets current probe, so the same thing, it's clamped on this wire just so you can see the actual load. There's current down here, but I wasn't sure if you could see it, so I thought I'd use that little clamp on. And then I have a scope probe. Finally, we're going to go look at the scope. But for now, here, let's zoom down and get a little closer look. Yeah, that's a little bit better, right? Okay, I'm going to go ahead and start bringing up the input voltage. And what I like to do is I like to see at what time, what input voltage that the output kicks on. If it turned on too early and we had a big load, it'd be a lot of input current. So you like to hold off the voltage to a certain point. So let's just see where this card holds off. Okay, you can see the voltage there on the meter here. Okay, there's 17. Okay, just before 18 it looked like it kicked on. Then I like to take it down to see at what point it turns off, to see what kind of hysteresis there is. $17.5. Wow, it's pretty decent. Okay, so I'm right around 15 volts. So I'm going to take it back up. Take it up to about 30 volts. So yeah, so that hysteresis, what that helps you for is if you're driving a load and let's say it turns on at 18 volts, but then the line impedance drops your voltage down to say a half a volt. Well, then your power supply would turn off and then the loss in the cable would go away. So your 18 volts would come back, it'd pop back on, and it'd just keep on doing that. So you have to have that hysteresis so that it'll allow you to have some cable drop on your input, or even if your input's coming up slowly and it's kind of not coming up smoothly, you don't want it to sit there and turn on and off your power supply at the point it turns on, right? So that's what that hysteresis does for you. Alright, so let's go ahead and apply a load now. Okay, we're on. Wow, we're up to 3 amps. This says 3 amps and this looks like it agrees, so pretty nice. Okay. Now that output just dropped out. So what I'm wondering is if it heated up that fast. I don't have any air flowing on this thing. It doesn't feel hot. Okay, let's go ahead and take it up again. Okay, we're at 4 amps. Okay, 5 amps. It looks like it drops the voltage. So that's only about 50 watts. Okay, had a little cockpit problem. What it was is my lab power supply, the current limit was set, and so you guys might have spotted that this voltage dropped out, which caused the output voltage to drop out. That is a common system engineering mistake. When you design a power supply, you send it off to the lab and they're testing it and they give you a call and say, hey, your thing's turning off. And it's a lot of times it's because just what I just did there. So let's go ahead and bring up the voltage again. Okay, and let's go ahead and start bringing up the current again. Alright, you can see we're at 2 amps. Okay, there's 5 amps, no problem. Alright, so we're up at, look at that, 7 amps. 8 amps, no problem. Now, I'm a little worried about that board getting hot, so let me just do a spot check. Wow, look at that. Doesn't look hot so far. Now, I aim to the left because there's low parallax there. See the lens for the thermal, and that's where the infrared light goes, or that's where the red light's going. So I just aim it to the left where I'm trying to see when I'm close up. So it's starting to heat up now. Okay, let's just go up again real quick. I think we're going to max out my... Oh, it's going the wrong way. Okay, we're 11 amps, 12, 13... What was that, 15 amps? Yeah, that's about as high as I can go with this. So, yeah, pretty nice, right? Okay, here, I'm going to take another spot reading real quick, just see. Temperatures don't look bad at all. Okay, let's see if we can turn this guy back on. I'll just take it to, I'm going to take it up to 10 amps. That's pretty high, right? Okay, 10 amps. Well, actually, that's 11 amps. Let's drop it down to 10. Okay, so 10 amps, 11.9 volts. So that's 119 watts, and we got 29.8 with 4 amps going in. Alright guys, that is about 119 watts input, and 10 amps times that, it's about 118, almost 119 watts out. I mean, that's pretty darn efficient. Okay, and here's what we see on the scope. Nice straight line. Now right now it's no load, 11.9, peak to peak is like 0, frequency. Okay, I'm going to hit the 10 amp load. You saw the line dip just a little bit. It says 11.9 still, peak to peak 160 millivolts. Okay, what we're going to do is we're going to AC couple that. And we'll put that up in the center of the screen and drop that down to, let's get rid of this stuff. Okay, that's 10 millivolts per division. Let me get a few more cycles there. Okay, there's some noise. Now, remember, I'm just got a scope probe up to the board. I'm not scoping it really carefully. Okay, guys, so I went ahead and put this little spring clippy on, and I put a few more cycles on there. So, yeah, that's the magic of getting rid of the line ground probe, which is just an antenna. It just picks up stuff. Okay, so now we're seeing some ripple here. Here, I can go back to kind of what we saw before. And you can see, some of this hairy stuff is still just noise, but the actual stuff that's a little wider is a little bit of ripple. Now that's 10 amps, by the way. Now, when I go 0 amps, 0 load, look at that. Now, when I had the other scope probe hooked up, it didn't matter if I turned off the load or not. I saw the same thing. So definitely an improvement here. But okay, let's go look at the spectrum. And by the way, when we're looking at this is 20 millivolts per division, right? Now, one thing a lot of specs say is to turn on your 20 meg bandwidth limit, because there's just a lot of that helps you clean up your stuff. So look at that. When we go to 20, it cleans it up. If I go to 100, even that cleans it up. If I go to 20, now let's put the load back on. See how that cleans it up? So that just helps clean up some of the probing, because we're cutting off the high frequency bandwidth stuff. But let's go put it back on for now, just for fun. Just leave it the way it was. Well, look, I'll go to 100 meg bandwidth. So you see a little bit more of it. Some of that might be real though. Okay, so there we go. Now let's go to the spectrum analyzer. Alright, so the spectrum is set up here. Let me just show you how it's set up. Frequency and span. So it's set to 1 meg, and start is 1 hertz. So we're looking from 1 hertz to 1 megahertz. And there's our noise, and this is 60 dB, so we're right just barely above 60. So 0 is about 1 volt, that's 100 millivolts, 10 millivolts, 1 millivolt. Okay, now that's without the load turned on. Here, let's get rid of this stuff, and let's turn on the load. Okay, that's 10 amps. You see it grow a little bit, and right here, 151 kilohertz is the highest peak, minus 44. And you can see the green thing bouncing around trying to decide which one's the highest peak. Okay, now here's something we can do. We go to search menu, and we can say, let's set the threshold, and see that orange line? I can drop that down right there. Then it shows all these peaks right here. I'll bring it right down so we capture a bunch of them. Okay, then let's go to peak table. And there's all the frequencies, like 30 kilohertz, 60 kilohertz, every 30 kilohertz. So pretty interesting, but yeah, it's not bad at all, guys. I mean, that ripple is down almost minus 60 dB. Hey guys, what do you think? Hey, you know what? I want to give a big shout out to EPC, Efficient Power Conversion, for sending this eval card. I think that was super cool of them. And it's a super cool running board too. You know, I didn't run it long enough to let it heat up, but it's pretty darn impressive that you can get that kind of power out without having to worry about a fan or anything, right? So, 2 thumbs up for this design. I like the GaNs, pretty awesome. Want to start using more of them. What do you guys think? Hey, I want to thank my patrons for all the support. Thanks everybody for watching the videos. Again, EPC, thank you. Oh, thumbs up to the video if you like it. Helps you, YouTube analytics, all that kind of stuff. And you can become a patron for as little as $1 a month. Just want to throw that out there too. Gosh, I might do some more testing. What would you guys like to see? Look pretty clean. I mean, it looks like a lot of spikes, but they're all pretty low. They're down in the millivolt range. So, but it's interesting that it's harmonics of 30 kilohertz, right? I thought that was kind of interesting. But all right, guys. Oh, and by the way, you know, there are 2 buck converters running at the same time, so I don't know if they're synced up. I haven't looked at the design close enough, or the controller, to know how it controls them. Sometimes it puts them 180 degree out of sync, but whatever it's doing, you might see extra pulses, because if they're both, say, running at 500 kilohertz, it might almost look like a megahertz, or they could be offset by 30K. Maybe that's why we're saying that. I don't know, but yeah. More investigation needed. Thanks for watching, and we'll see you next time.